Okay, so I will first demonstrate the direct functionality of the card module, and then I will demonstrate the interplay between the client and the card. How the client generates the transaction that is to be signed, and then the card gives the signature to the client, and then the client generates the final transaction, which is to be put onto the blockchain. But first, we're going to go through the instructions I'm going to send the card. So I'm going to send these two instructions, which represent the uncompressed and compressed public keys. Then I'm going to get the address bytes of that specific public key through this instruction. Then I will assign a random nonce, which is a random 32 byte number consisting of the byte 01, which just means 1. So it's just 010101. So I'm going to sign this and see what I get. I should get a valid signature. Then I should sign transaction bytes. Now obviously I should put like an actual transaction here, but these bytes in the middle, so I'm going to highlight them right now. These are the transaction bytes. They'll be pretty random, and it doesn't matter. And then I'll check if the wallet is secure. It should not be secure because I've already signed a transaction, and who knows what I'm going to do with the transaction. So obviously the wallet is no longer secure. Then I will reset the wallet, which generates an entirely new credential for Bitcoin in order to make it secure. I will recheck if the wallet is secure. This time it should be secure because no transaction on this new set of credentials has been signed. Therefore the wallet is entirely secure. And I'll get the new uncompressed and compressed public keys, and I'll also get the new address. Now if I run all of this and I follow along, I should get the uncompressed and compressed public keys. Here's the uncompressed version, and here's the compressed version. As we can see, this portion, FA, FA, 05, 05, ED, ED, OA, OA, and so on until here is the same. Now the second part is compressed into this prefix of 02 through some weird fancy cryptographic stuff, so it works. We also get the address bytes with the 6F prefix, which is indicates that it belongs to the Bitcoin test network, so that's correct, that's good. Then we sign a random nonce, which is the 32 bytes or whatever, and we get the resulting signature here. It starts off with 3046, which is an indicator that it is indeed a signature. It signifies a compound structure of length 46. 46 is obviously in hexadecimal, so it's way more than actually 46, and so on. And we then sign a transaction here, and we also get another signature, and this signature would be used to put back into that transaction and so on. Now once we sign that transaction, we should get the result for whether or not the card is secure, and obviously we get 00, which means no, false, it's not secure. And if it was secure, we'd get 01. We reset the card through this instruction, and this output just means everything went fine. It's at the end of every correct every return value that's correct, you would get 9000. So we ask the card whether or not it's secure now after it's been reset and has a brand new set of credentials, and it returns 01, which means yes, it is secure, and obviously 9000. Then we after we do that, we get a new uncompressed and compressed public keys. So if we compare the compressed public keys at least, and we check this with the one we had before, they are different. Firstly, this one starts with 02, this one starts with 03, so that's at least one difference. And again, new address bytes, we see that indeed it's different because it ends with A8 and the other one ended with 98. However, they are both 6F in the prefix, which just indicates that it's the Bitcoin test network, which means these are valid addresses. The direct interaction with the simulator of the card works, so the card software works. Okay, so now is the part of the demonstration where I show how a good valid transaction can be generated via using the client which interacts with the card software. So here we have the address. This address is representative of the credentials held by the card on the first time that it initializes. I already tried out a lot of it. So for example, I have 4 outputs that I've spent already to this other address here to try and test it out to see if it works, if there's any bugs, and fortunately there are no bugs, and so it works. So I have one more output to spend, and I will spend it right now by running the client code like so. It will fetch this exact thing, this exact transaction, and I will enter the fee of 192 Satoshi. This is going to give me approximately 1 Satoshi per byte in terms of cost for the transaction. I will enter that and I will get a signing message template. Now I will simulate via copy pasting what the client will do in order to communicate with the card. Now because I don't have a physical card, I would have to copy and paste this, but if there was a physical card, these bytes would be physically transferred via some sort of wire from the client into the card as so. But because we don't have that, because it's simulated, I'll literally have to do that by myself, and I will paste it right here, and then I'm going to run this in order to sign these transaction bytes. Now when I run this, I get this signature right here. I'm going to copy the signature. I'm gonna paste the signature back. Now what I'm doing here, where I'm pasting it back, is basically what's gonna happen if there was a real card that was communicating with a client, where all these bytes would literally just be transferred to the client without having to copy paste it. But because I don't have the card, I'll have to do this manually for now. But once I do this, I get the final transaction bytes right here, and hopefully no errors should occur. And if I paste it in, I broadcast the transaction, and it says this because well, obviously because the blockchain hasn't updated. But if we wait for a while, there we go, it shows up, and right now it's unconfirmed, and it's about one Satoshi per byte. But if we wait for like maybe 10 minutes, it will confirm itself, and I can show up here on this address. In fact, if I refresh both of these, there's an unconfirmed spend of that output I was talking about, and here it's an unconfirmed receive of that specific output minus the small fee I paid for the transaction. And in 10 minutes ish, there will be a confirmation, and I will be able to 100% settle this. Okay, so after a long while, around 14 minutes, I have one confirmation, and that's enough for the blockchain to count it. After like a couple of hours, it will be 6 confirmations, which means it's like definitely 100% real, and it's a definite transaction. But I'm not gonna wait that long, because unless like something absolutely catastrophic happens, this number right here will increase from 1 to 6 as it should. Refreshing these addresses, we see I have now 5 outputs that are confirmed received, and 5 outputs that I've spent,
and no outputs that I've not spent, which is different from what it was before, where I had exactly one that I did have to be able to spend it. And if I look here, the latest transaction, which is this one, is sending 0.77 Bitcoin, the one that I had, well, 0.00077, and transferring it to this account, MRQPJ, and so on, which is this wallet. And so it shows up on both of these wallets. So clearly the transaction has been a success. The client is working, the card is working, and I think that's a good first draft to have.